So real quick on the top here, hopefully you're comfortable with most of these things. Charge and current, how do you solve for the amount of time it takes to charge pass through? That's that one equation, I equals Q over T kind of thing. And then also how many electrons pass through. The one constant you'll need is the number of charges in a coulomb. I will give that to you on the test, so don't worry about that. Resistance in Ohm's law. What does the resistance depend on? Remember, it depends on length, the type of material, the area. What does it mean to be ohmic? What's a good analogy to think about when you're asked about resistance? It's the opposition to the flow. What's the difference between potential difference and voltage? Not really anything. This is the quantity. Voltage is technically the unit, but we tend to use them interchangeably all the time. Can resistance ever be equal to zero? The answer is yes. We call that a superconductor. How do you solve for power in three ways? Remember IV, V squared over R, I squared R. Schematic diagrams, are you pretty comfortable with series and parallel? We'll do some practice on these in a second. And then circuit tools, how to use an ammeter, how should it be arranged in the circuit, what's the purpose of voltmeter, and how should it be arranged? Remember back from your lab doing that kind of stuff. So those are the big ideas in this chapter. Here are the equations I'm going to give you. Those are on the sheet. The one thing that's not listed here is the constant, how many charges in a coulomb. I'll give you that number so you don't have to memorize it. But keep that one handy real quick, and let's take a look at a couple of these. Here's the first series of practice problems. Last time I had you, we did a couple as a group, then we did some as a class. Do you want to do the same thing here? So like, for example, do these three as a class. Do the next two questions as a table. Are you good with that? All right. So let's take a look at these together. And forgive me, I'm going to be writing on the screen here. So first of all, what we always do is identify our variables. In this case, we have the current. What's the variable used for current?
Amp.
Yeah, units amps. The variable? I. And how long does it take is what we're trying to find. How long does it take is another word or way of asking for T, time. And then finally, 3.5 coulombs is really, what is that? Yeah, it's the charge. Represented by what variable? No, I's current. R is resistance. Yeah, Q, good, is charge Q. So immediately you should go look back at your table. What equation has I, T, and Q in it? Yeah, and you're like, Ms. Calmer, it's too easy. I know, forgive me, I'm going to go do this slow. Yeah, current is defined as the rate of flow of charge over the rate of flow of time. And so we can actually solve this. Whoops, sorry for my splotch there on there. We know the current is 9. We know the charge is 3.5 coulombs, and we're looking for time. Mathematically, how do you solve this one? I need to take 3.5 divided by 9. Sorry, get my calculator out. Multiply both sides by t, then divide both sides by 9. The time I get, and could somebody double check my math? As I'm trying to do this quickly while trying to draw on this at the same time, about 0.39 seconds is how you would solve that. All right. 2, how much current, so we're looking for current again, and just learning the variables is probably the hardest thing in this chapter because you're like, oh, current should be C. Current's I, and we have resistance. Remember, oh, sorry, I shouldn't have said that. 10.5 ohms is the unit for resistance. And we have this. What's this? Yeah, it's voltage or electrical potential. It's V. What equation from your periodic table? Ohm's Law is probably the one you want to use. So in this case, I'm fixing this one while we're at it real quick. Ohm's Law is the one that relates current, voltage, or electrical potential and resistance. And so we can actually solve this real quick. We're actually solving for current this time. The electrical potential is 120. Forgive me for not writing all the 0.0. I'm trying to write as quick as I can. Divided by the resistance, 10.2. And could you grab your calculators real quick and just make sure I did my math right? Because I'm trying to do it as quick as I'm trying. You got 11.8? I agree with you. Excellent. Thank you. I hate to make a recording and send it to people, and then they're like, Ms. Clomer, you did the math wrong. Yep. All right. Good. Third one, an ammeter measures this. Again, the variable for amps is I. And we have electrical potential represented by V. And we're looking for resistance, which is R. Again, Ohm's Law should immediately come to mind. You're like, wait, Ms. Clomer, this is not bad. Yeah, as long as you identify what you know and what you don't know, it's usually pretty straightforward. In this case, a little bit more complex math. The current is 2.5. The voltage is 9, and we're looking for R. Are you all comfortable with the algebra going from here to solve? Multiply both sides by R to get out of the denominator, then divide both sides by 2.5. And somebody check my math. I get could you? Resistance 3.6 ohms? Okay, shoot, good. Good. Everybody there? Can I go to the next slide? All right. So on this slide, these two questions, I'd like you to try as a table. Work on this together, and maybe the two of you could work together as pair. Could you please try these two? While you're doing it, could you do it kind of quietly? Because what I'm going to do is do it live on this. So if you get stuck, you can look at the screen because you're going to see exactly what I'm doing. Or should I freeze it so you don't see?
Yeah, you should freeze it.
I should freeze it. All right, so I'll do mine real quick, and then you can check your answers. Work with your neighbor real quick, and I'm going to do it simultaneously with you. Oh, this one's schematics. Ooh. Draw a circuit diagram containing a battery and two light bulbs in series with an open switch. Ooh. All right.
I don't think we ever learned about switches.
Yeah, if you look back in your notes, you'll find a picture of a switch. But you're right, we never actually drew one with a switch.
How do you draw it?
Yeah, I'll tell you what, I'll unfreeze so you can all watch at the same time. So there's a battery. The plus end is always the long end. And I just have a bunch of them. Like, Ms. Clomer, how many should I draw? The answer is not critical. Here's what a switch looks like. That's a switch. So right now it's open. And all that happens here is normally when you close a switch, you move this little piece down here, which completes the circuit. And you've got two light bulbs in series. Are you good? Can you take it from here?
Yeah.
Okay, I'm going to freeze mine again. So try this real quick. Draw the two light bulbs in series. So you have to remember the difference between series and parallel. Yeah, symbol for a light bulb, a couple different ways of drawing it. I'm going to draw mine this way. You'll see it in a second for those of you in class. And then show the direction of electron flow. Oh, that's tricky. So electrons are going to be flowing around the circuit this way. Not the direction that we normally draw current going. But yeah, electrons are going to be going around the circuit in this direction. And then question 5, I just read it, is actually kind of confusing.
Two light bulbs in parallel, one pathway.
With one pathway, it means to one light bulb with an open switch like we drew up above, and then one with a closed switch. That would mean the little flap thing is actually closed. You got to do two switches on this one. And again, show the direction they want of electron flow, not the direction of current. Yeah, it's not too bad. I'm trying to draw straight here.
So I'm gonna go with this.
What with a closed switch? So here's my closed switch. It's actually making contact. And a light bulb. Back down. And the other one with an open switch. Like this. So what's going to happen in this circuit, when you first turn it on here, only that first light bulb is going to light up because it has a switch that connects it.
Does it matter if it's first or second?
No, it doesn't matter. And the second light bulb won't be lighted until you actually close that second switch. Oh, and they want to show, again, you're showing the direction of electron flow. So backwards. And I'll show my answer in just a second. Have you had a chance, for those of you in class, to talk to each other?
Yeah.
And I'll show you my answer in a second. Would one of you want to show the answer on the screen? Or do you just want to? No? Okay. Fair game. Are you ready? All right. Here's what I have. So mine looks something like this. Just let me quick explain it for those of you who are in the classroom. So light bulbs in series, one after another. You're like, Ms. Comer, I drew mine with a different filament. That's fine. Something that looks around here with filament in it. And then the idea of an open switch. This is the symbol for a switch with it open. You would normally close it by moving it down. Which way are the electrons going? The electrons would go from the negative terminal to the positive terminal. Remember, what direction do we normally draw current? Going from positive to negative, Ben Franklin, the conventional way. And then the bottom one is the two light bulbs in parallel. One pathway with a closed switch and the other pathway with an open switch. So here's a switch, but this one's closed, actually making a connection. What would happen in the bottom case here? The light bulb with the closed switch would be lighted. I don't know how to show that. Show light coming off of it. And the other one would be off unless you close the switch. Both of these would be lighted, so not so bad. I suddenly feel like I'm coloring. There are lots of different ones. The top bulbs would both be on. The bottom circuit, only the one that's like that. Sorry, unfortunately the ones we did together as a class and the ones I just had to do as a table were very different, non-mathematical. These are more drawing ones. Yeah, this kind of stuff's on a test. Don't worry. Easy ones. Are you good on these?
Is this
All right.
considered easy?
Yeah, except we've never done switches before. But you drag these things around, but instead of resistors this time we're dragging around light bulbs kind of idea. Yeah.
Does it matter if we put the light bulbs on the side on the first?
No. So yeah, but you could have drawn this one. I should have actually put it. You could have put the light bulbs like this on the first one. It doesn't matter where you put them.
You could put them up and down.
Yeah, you could put them like one here, one going down, would be absolutely fine. Like, wait, could I even draw it like, one light bulb going this way, a wire with one light bulb going this way? Yeah, this is fine too. The idea is that you just have, the current's got to go through one light bulb and then the next. But any of those ideas would be perfectly fine. All right, so here's the question I'd like you to try individually with a little bit of schematics. This one actually has two pictures, and I just want to quickly draw your attention to this one because it seems confusing. This wire here from the battery goes to the side of the light bulb, connects there, and then it goes from that side there to this one here and connects to this side. The other wire goes to the bottom of both. Both of these light bulbs will light. And in this one here, if you can kind of see it, one lead of the battery is going to one side light bulb, one lead to the other. Draw the corresponding schematic diagrams for these two. So redraw them like we drew the previous ones. And should I give you a hint? Which set of these light bulbs are in series? Which ones are in parallel? It's actually a trick question.
They're both.
They're both what? They're both in parallel. If you can't see it, they're both connected, both directly to the battery side by side. It may not look like it, but they're both in parallel. I'm going to freeze my screen. Could you try this one on your own? Don't panic. If you get stuck, it's okay, because I'll show you the answer in just a moment. I'm going to freeze the screen and draw it on here so the people on the recording can see it.
There's no like switches there.
No switches this time, so pretty doggone easy. And you're like, wait, this can't be this nice. It is. And there's a multitude of ways to draw this one. So don't worry, there is no single right way. But go ahead and try both of them, if you would, please, and then we'll take a look at both of them together. Give it a shot. It's not as bad as you might think once you get the sort of feel of this. My apologies in advance to those of you watching the video on this one. I am being very slow in my drawing skills. I am not fast. Did you get it already? Sure.
I think I got it.
Do you another, for those of you in class, do you need another minute? Not getting it? Okay. All right. You ready? Even if you're not ready, let's go take a look at it. It should look something like this. Let me just quick explain on this one. Both light bulbs are connected to the positive terminal of the battery. So 2 light bulbs both connected to the positive lead, and then both of them are connected to the other negative lead. You're like, Ms. Clemmer, I drew it just sideways or something else. As long as they're both connected directly to the battery, it's fine. The second one, same thing. All 3 of these light bulbs are connected directly, one lead to the negative terminal, one lead to the positive. This time I actually drew the cell as like 2 sets of long lines, 2 sets of short lines, because there were 2 batteries over on this one. You're like, Ms. Clemmer, are you going to be that picky? No. But I thought, especially for the video, I should probably be picky. This one has 1 battery, 1 cell. This one has 2 cells, so 2 sets. Something like that. Are you feeling okay on these? Yeah? Okay, all right. Schematics are a little bit tricky. Now we move into the resistor ones, which is the one I'm most worried about. I'd like to do this one together with you, if you would, just because it's a big enough change. Or do you want to try it on your own? All right, the 2 questions on this one is, first of all, calculate the total equivalent resistance of this whole circuit, and then the total current passing through the circuit at the battery voltage 12 volts. All right, let's take a look at this one together. First thing I'm going to do, just for my own sanity, is draw all the voltages on and everything on here, because I can't think otherwise. So the battery is 12 volts, and resistor 1 is 15 ohms. Resistor 2 is 10 ohms. Trying to fit this in here without running over everything. Resistor 3 is 5 ohms, and the other one is 20 ohms. First question is, what's the total resistance of this circuit? Where should I start, for those of you in the room? Which one should I add first? Yeah, the 2 in parallel. Good choice. These 2 right here, I should do first. And if you look back at your formulas, these are parallel when they're side by side. In fact, if you look at it, it almost looks like a parallel symbol, side by side, except vertically. So how do you solve this one? Well, for this one, 1 over R equivalent, trying to write an EQ really small, will be equal to 1 over 10 plus 1 over 15. To add those 2 together, I'm going to do common denominators. And the only number I can think of is 30 off the top of my head. So multiplying the first one by 3 over 3 to get 30 in the denominator. Remember, to add fractions, you got to have common denominator. And then the second one is 2 over 30. And now I can add those two fractions. Multiply the second one by 2 over 2. I get 5 over 30. Or I could reduce that down to 1/6. But again, remember, that's not our final answer. That's the reciprocal of the resistance. So what is the total resistance of this blue box? 6 ohms. Okay, sorry. Maybe it's good that I'm writing so slow because I have to actually draw this all out. So this whole thing is 6 ohms. And now we can actually solve A. What's the total resistance of the circuit? Well, this whole blue box is 6 ohms. That's in series with this 5 ohms and 20 ohms. What's the total resistance of the circuit? Well, in series, you can just add them together.
31.
Yeah, which is a really horrible number. So 6 ohms, our blue box, plus the 5 ohms, plus the 20 ohms. Yeah, yuck. All right, I guess I shouldn't complain. But yeah, the total resistance is going to be 31 ohms. And then finally, what's the total current passing through the battery? So we want to know how much current is coming out of here. What are we going to use? Good old Ohm's Law. Resistance was the hard part. Now this is the easier part. We're looking for current. We know the voltage. Oh, actually, I should write it out again. We know the voltage. We know the resistance. We just found it. And we're looking for current. Oh, shoot. Dang it. And so, of course, the equation you want to use here is something that includes resistance, voltage, and resistance. Yeah, good old Ohm's Law. It's just going to be equal to V over R. And in this case, 12 over 31. What horrible numbers. I know you just solved it. What is it? 0.39. Or
Yeah.
0.39. Yeah, we'll just call it 0.39. 0.39 amps. We probably should go to 3 sig figs, but close enough. And you got it. Are you okay on that one? Finding the total resistance on top was the hard part. The second part, not so bad. All right, let's take a look at the next problem. Are everybody good on this one? Okay. Next problem. Oh, you got to draw a diagram. A circuit has a battery with potential difference 12 volts, a resistor with a resistance of 5 ohms, followed by 3 parallel branches, each holding a resistor of resistance 9 ohms. Diagram this circuit, calculate the total equivalent resistance of the circuit, and calculate the total current. This is the one I want you to do as a table. Do you want to do A together as a class, though? Okay, let's do A together as a class. So drawing the diagram, first of all, it's a little confusing. You've got a battery, first of all, but it doesn't matter exactly. I could have drawn this battery horizontally as well. I always just like drawing them vertically to get started. And then it goes through a single resistor. That is 5 ohms. That's this first part. So I'm just kind of reading through the sentence one piece at a time. I guess I should label this. This is a 12-volt battery. And then this next part. What in the world do they mean? And it followed by 3 parallel branches, each holding a resistor of 9 ohms. I could draw them vertically like we did the other one with the 3 light bulbs. Just for your sanity, in mind perhaps, I'm going to draw them this way. And I think you might see why afterwards. Yeah, go ahead.
If you draw it the other way, like in another diagram, will that be like...
It's still absolutely right. Yeah, I'll draw the other way just in a second, but I'm drawing it this way because I think it might be easier for all of you to solve. And I think you'll see why in a second. So I'm going to put all of these 9 ohm resistors like this. And sorry, trying to write them in there all like that. You could have also drawn the circuit like multiple different ways. You could have put the 5 here, and then these all side by side over here. and that would also have been fine. In fact, there's a whole almost infinite way of drawing these. I was just trying to make it as obvious as possible. But yeah, that would have been fine too. I'm going to draw it this way. Could you please try B and C? Actually, do B together first as a table. Could you please find the total resistance of this one? In this case, let's go stop real quick before we get started. Which ones do you want to add together first? Yeah, the parallel ones, the 3 9-ohm ones. Could you please do these first? And then figure out the total. And at this point, I'm going to freeze my screen. Could you please talk to your neighbor real quick and just try to answer B on this one? What is the total equivalent resistance of this entire circuit? And I'm going to do it simultaneously, sort of quietly on the screen here. But yeah, to do this, 1 over R equivalent is going to be 1 over 9. Oh, at least the fractions are nice this time. Yeah, this makes... Actually, they still didn't make... I wish they made the 5 ohm something different, but that's all right. 3 9ths, or reducing that fraction, gives us 1/3. And since that's equal to 1 over the total resistance, taking the reciprocal of 1/3 means this whole thing is this many ohms. So then what's our total resistance for B? The total then, for things in series, you can just add them up. Did you get an answer for B? Yeah, good. I'll show it on the screen here in just a second. You're doing faster than I can even write. If you solve this, the resistance in parallel should be 3 ohms, and then that is in series with the 5 ohms. Total resistance of this circuit is 8. Agreed with each other? Good, good, good. And then finally, could you try C together as a table? What is the total current running through this circuit? And again, most of you can probably figure this one out very quickly, and I'm talking to the people on the screen. You're trying to find current. Ohm's law is a logical choice. So solving this one, reducing that a bit, that's 3/2. So it should be, if I'm doing my math right, this. I guess I should box all my answers. That's a decimal point, believe it or not. Did you get C? Ready for me to show? I hope if I did my math right. Did you get about 1.5 amps?
Yeah.
Nice. All right, good, good, good. I think there might be one last one in here. Yep. There are 3 resistors in a circuit. Diagram this circuit with the resistors in series and calculate the total equivalent resistance. And then diagram this circuit with the resistors in parallel and calculate the equivalent resistance. Your choice on this one, for those of you in class, this one is our last one to do together. Do you want to try this one individually, or do you want to do it as a table? This was supposed to be an individual one, but I don't want to overwhelm you. Table? Or try it individually, but talk to each other about this one. While you're doing it, I'm going to quick freeze. Zach, could you hit the air conditioning, please? Thank you. Yep, just hold that in for a moment. All right. So this one is the one in series. And you could draw it a bunch of different ways. I'm going to, just for change, instead of drawing them all in a row, do it this way. Just to show you it doesn't actually matter. Wire length is irrelevant. It also makes it a little bit more compact in my case. So there's the 9 ohms. It actually doesn't even matter what order you put them in. It doesn't matter. It's associative. You'll end up with the same result each and every time. What's the total resistance of this circuit? Well, actually, you actually don't even have to include the battery. I did anyway. I just assumed there was a battery in it. In this case, just the sum of those. And if I'm doing my algebra correctly, that should just be this. Are you ready for A? Okay, I'll wait a second. I'm actually going to remove. I just erased the whole thing. Sorry, I'm going to have to redraw. Now I need a minute. And forgive the fact that I'm redrawing these very, very quickly. All right, got it? What'd you get for the resistance for A?
39.
Good, should be 39. All the ideas here, one resistor after another. I drew them just differently, just for fun. And then finally, could you try B? Again, either individually or together. Sure. Ooh, yuck. Oh no. Sorry, I'm just trying to do the common denominator in my head real quick. Did you solve it already? Oh, you got it already. Dang it, you're so fast. It takes me so long to handwrite this on my trackpad. Oh, right. 72 would work. What did you use? 30?
36.
Oh, 36. Oh, that's much easier. You're right. All right. Do my math here real quick. Oh, shoot. I just wrote that. Shoot. Let me fix that real quick. As I was talking, I was writing at the same time. That one should be 18. Using common denominator of 36. 4, 3, 7, plus 2, 9, 36. Or reducing it 1 over 4. But remember again, that is equivalent to 1 over the total equivalent resistance. So what's the total in this one? Should be this. You ready? Yeah. Did you all get it?
Yeah.
All right. Answer is, should be 4 ohms. Pretty good? All right. Sweet. And that is 1,500 kilowatts of power to an electrical generator that converts 95% of this mechanical energy into electrical energy. What's the current delivered by this generator if it delivers energy at 3,600 volts? So here's what we've got here. We've got power, and we've got voltage, and we're looking for current. Why is this one so horrific? You're like, oh, wait, this is easy. We're looking for current, I. You're like, oh, this is just one of those power equations. Yeah, in fact, power is equal to current times voltage is the one we're going to use. What's the twist in this one? This 95% is the twist of this one. Why? The power here that we're going to plug in here is 95% of this. So what's the actual power going to be? 95% of that. So it's going to be 4,500. And I'm going to write it out. Kilowatts is actually 1,000 watts. So 4,500,000 500,000 watts times 0.95 or 95%. So the power in this case is going to be 95% of the energy coming into the generator. The voltage is exactly what you would think, is 3600. And you're going to solve for the current. And did somebody already solve for the current? It should match whatever answer it is, but hold on a second. Let me, I'll quick do it. So, is it, okay, 4.5 exponent 6 divided by 3600. Yeah, so you get a current of, I get 1250 amps. Which, if I had to choose an answer based on that, would be C. Is that what the answer key has? I hope. Okay, phew, good. So they went to 2 sig figs, although they rounded down. But yeah, somewhere right around there. But 1250 would be the exact answer.
So 4,500 kilowatts is 4 million.
Yeah, kilo is 1,000. So yeah, adding 1,000 behind it. So 4,500 with an extra 1,000, 4,500,000, or 4.5 megawatts. Yep.
I'm not getting 1250.
I got 11.
Oh wait, maybe I did my math wrong. Hold on.
I got 11.
Oh shoot. I actually.
I guess you can round it.
No. I did. Sorry. Thank you for catching me. I forgot to multiply by the 95%.
Dude.
Dang it.
But the answer key still says.
Yeah, the answer key would.
Works because
It would.
it's 1200.
Yeah. So
It rounds up to 1200.
if you had to choose, I guess. Yeah. I guess if I had to choose, it's closer to that than it is to that. But yeah, you're right. If I rounded to 2 sig figs, I'd end up with 1.1.
No, that's not what we got either.
That's not what you got either? Hold on.
1187.5.
Oh, 1187. Okay.
So then you round that up.
Yep, sorry. That is right. Okay. Sorry in my haste. Yep.
Jeez, bud.
Wow. Phew. There we go. Sorry for those of you watching at home as I make all the mistakes. It's about 2.5 amps when connected to a 120 volt socket. Assuming electrical energy costs 6 cents per kilowatt hour. There's a couple of ways of solving this one. One way is to calculate the number of kilowatt hours, which is literally taking power times time, but power in kilowatts times that. Or if you remember back from our notes, 1 kilowatt hour is actually equal to 3,600,000 joules, 600,000 joules. We could also figure out the amount of energy the television uses and then convert that into kilowatt hours. I'm not sure which is the easiest way. I think I'm going to try this way first. So to figure out the number of kilowatt hours, I need to figure out, first of all, how many kilowatts this thing is using, the TV is using, how much power, and then multiplying it by 8 hours to get the hour part of this thing. To do that, if it's using 2.5 amps when connected to this voltage, I'm going to do power is equal to I times V. And so in this case, power is going to be 2.5 amps times 120 volts. Is it 300? It sounds like 300. It should be 300 watts. Good. So that should be 300 watts, which is pretty typical for a fairly large flat screen TV. But to use this equation, I need to convert it to kilowatts. A kilowatt is 1,000 watts, so I just need to divide it by 1,000, and so this ends up being 0.3 kilowatts. So then how many kilowatt hours does it use? I just need to multiply how many kilowatts it uses times how many hours I'm using it, which is the 8 hours. So the kilowatt hours, which is a strange thing, strange unit, only used by power companies, is going to be 0.3 times 8 hours. The 0.3 from the number of kilowatts we just calculated, the 8 hours from the question itself, means we end up with 2.4 kilowatt hours. And then to figure out the total cost, we just need to multiply that by the cost per kilowatt hour. If you want to do a quick fraction on this one, we know that the cost is 6 cents per kilowatt hour. So if you just multiply it, here's our equivalent thing, is equal to 1 kilowatt hour. Kilowatt hours cancel. And 2.4 times 6 cents, I need to get my calculator, is not too expensive. Oops, give me a second. 2.4 times 6. Oh my goodness, it's going to cost us a total of about 14 cents. The closest answer up here, I would probably go with C, 14 cents. It's B? Oh wait, no, okay, somebody else saying B. Okay, just C, good. And that should give you your answer.